Now, to get to structure 3 C3 star, okay, we have to backtrack a little bit to the very beginning when we were still just creating our chair cyclohexane structure. And let's recall that we began by putting 6 carbons in a ring and we created this boat structure. And only after we formed that boat, we decided to take one of the, I guess, helms of the boat and we flipped it down to be able to create the chair or the sun lounge version of cyclohexane. This tells us that cyclohexane, like a lot of alkanes, has some level of mobility. So there's some level of rotation that can happen with its bonds. No? But unlike open chain alkanes, like the ethane molecule that you dealt with in part B, you cannot fully rotate the bonds. And an extreme example of how in a cyclic compound you can't rotate bonds at all was when you made your cyclopropanes in the earlier part of part C. Now, because cyclohexane is such a easygoing system, there's not much angle strain. In fact, if you were creating it, you should have noticed that it was a very less tedious task than creating the 3-membered cyclopropane. That means that the cyclohexane chair is quite wobbly, and in nature it really does wobble and flip around a lot. Okay? Now, just like with ethane, however, we do not actually break any sigma bonds in wobbling or flipping or twisting bonds. What's really happening is just we're creating different conformations of the same molecule. Okay? So if a boat can become a chair, that means that a chair can also become a boat. And then that boat can also become another chair. So let's go to the second one. In structure C3, you already have a chair. And that chair, we're going to turn it into a boat. And then we're going to turn that boat into a chair. So let's look at this structure right here. This is structure C3 that we had. Remember, the headrest has this red hydrogen going up. You have the axial up red hydrogens. You have the axial down yellow hydrogens. You have the equatorial blue and green components here. Okay. Now what we're going to do is that I want you to be able to properly spot where your headrest is, and where the footrest is. Again, headrest will have one of these carbons with the red, and the footrest will have one of these carbons with the yellow hydrogen going vertically down. So there, I don't know if you can see it, that zigzag going down. It's this, up, down, here, okay? What I want you to do is that from this chair, we're gonna flick the footrest back up so that we can create a boat. And if you can see the boat, that's good. If you can't, try your best. Now you'll notice that in creating the boat, you'll have this red and this blue come close to each other. Does this tell us that a boat is more stable than a chair or less stable than a chair when you have these two components really near each other? Okay, so once you've put your footrest back up to create the boat, I want you to take the old headrest with this red carbon and now flick it down to become a footrest. Okay, so the old footrest is now a headrest, and the old headrest is now a footrest. And I just want you to adjust certain things and wobble it around. And when you do that, you'll end up with another chair. But this other chair will be oriented the other way. So now this carbon here with the yellow and the blue is now your headrest carbon, and this carbon here with the red and the green is now your footrest carbon. Okay, so let's just repeat that again. Okay, let's go back to our original structure. Okay, red, axial up, yellow, eggshell down, blue and green are equatorial. I'll take the footrest, yellow and blue carbon. I'll turn it back into a headrest to create a boat. We're here, chair boat. And then we'll take the old headrest with this red and green and we'll flick it down to become a footrest. And in doing so, I want you to jiggle it a little bit so that now you'll have 3 blue hydrogens in an eggshell up position, and I want you to have 3 green in an eggshell down position. And then this time, all of the red and yellow components are the ones that will be in the equatorial position. Okay, so it's interesting. A while ago, all of the reds and yellows were the eggshell, and now they're all the equatorial. And a while ago, all of the blues and greens were in the equatorial position, and now they're in the eggshell, after performing what is called a chair flip. So let's go ahead, and I'll just show you on paper how that looks like. Okay, so let's just recall. Our footrest becomes the headrest here, and our headrest, let me just encircle that green, will now become the footrest after a chair flip. All of the blue components, the blue hydrogens, are the ones now going vertically up. So, and one of them is coming out of the headrest. So this one. And just like with all the other eggshells, they go every 3. So, sorry, every other carbon, there's going to be an eggshell one going up. So 1, 2, 3 here going up. 1, 2, 3 here going up as well. Okay, and between these there are going to be green ones going vertically down. So on the footrest now here, this one is the footrest where my finger is. It has a green hydrogen going vertically down, and the same thing will happen every other. There's going to be a green thing going vertically down, a green hydrogen. Okay. And what we're going to do is we're going to fill in the missing equatorial, okay? So on all the carbons with the blue hydrogen on an eggshell up, you'll have an equatorial down hydrogen. Oops. And on all the carbons with a green eggshell carbon, or hydrogen rather, you'll have a red equatorial. If you don't know what directions to draw these in, again, there is a video in your module that will guide you on how this will happen. Let's pay attention to what happens when you take a certain original form of a cyclohexane molecule, you perform a chair flip on it to create its chair flip isomer, or its other chair flip conformation. Okay. In your answer sheet, I want you to not just say that we performed the chair flip, but I want you to be able to describe what happens exactly. Okay, and this is going to be your guide to answering it. Let's recall the parts of a chair. Okay. In our original form, all that were in red were in the eggshell up position. All that were in yellow were in an eggshell down position. all in blue were called the equatorial up positions. And all that were in green in our original structure were all in an equatorial down position. Now let's look at the chair flip conformation. If you look properly here, okay, or maybe here on the footrest of our new chair flipped form or chair flip conformation, you'll know that the red is no longer in an eggshell position. It's now in an equatorial position. And the green is the one now in an eggshell position. But the green is in an eggshell down position. And the red is an equatorial up position. If we compare it to their original forms, green was originally equatorial down and it became eggshell down. Red was originally an eggshell up and then it became equatorial up. With that, okay, I want you to look at what happens to the yellow and to the blue and try to come up with a set of rules of what happens when a chair conformation flips. Does the equatorial or eggshell-ness of a substituent change? Or is it the being up or down that changes? And if so, can you devise a shortcut of how to make a chair flip? Because for our last pair of molecules, for C4 and structure C4 star, you are now going to actually test your chair flip conformation skills. Okay?